Thank you, Hervé. Thank you for your invitation. I will talk about Mars through the eye of past habitable environments. So habitability on Mars is a big deal. Find life, find organics. I will not talk much about organic. It's not my specialty. As a geologist, I work more on the environments. So rivers, lake deposits, everything related to past environments. So we will focus the lecture mostly on past environments, just a few words about recent environments, but mainly looking at very old rocks, both from orbit and from rover data. And to start, just a very short word about Earth, because on Earth, you know the rock cycle, we have life almost everywhere, from the surface to the sea, at the depths, around volcanoes. So where life is, and we don't know where it forms, but it is propagated everywhere. So on Mars, we are looking for life, but we cannot know where, if it started, where it could have started. So we will look at any places where it could have started, or it could have developed or be preserved. And preservation is very important for a geologist because the preservation is not always the location where life has started. It could be in sediments far away from where it started. But preservation is where we can collect rocks and analyze rocks. So it's also important to consider that the environments I will show is not always the environment where life was started or developed, but the environment where we can preserve organics and just get rocks to sample. In this lecture, I will first do a small starter with how to analyze Mars, because we have orbiters, we have rovers, how we do take data at the surface of Mars. And then a first part will be the longest here. It's all about aqueous sedimentary environments, especially on ancient Mars. Then we will move on to the surface with weathering systems, and then move up depths with hydrothermal environments, first at depths and around volcanoes and impact craters. So as an approach to study past habitable environments, we need to have as much data as we can. Of course, we are not on Earth, we cannot collect data easily, we cannot sample rocks easily, so we need to collect any information we can have from the surface of Mars, both from orbit or from the surface. From orbit, we have images up to 25 centimeters per pixel that enable us geomorphic interpretation. And in the same morphologic and sedimentologic conditions, we also have rovers which tell us a lot on the texture and the facies of rocks at the surface. On the other hand, chemistry and mineralogy are really key for many indication of chemical conditions and also minerals that could preserve the organics, for instance. We can have orbital data with mineralogy that's made with spectrometers in orbit. And we can also have in situ observations from rovers telling us about the chemistry and the mineralogy. So coupling both approaches is clearly what we need to do to define the environmental conditions of early Mars. So how to analyze Mars from orbiter? To the left is an high-res image, 25 centimeter a pixel. You can see layers. These are sedimentary layers, and there are tons of wonderful images of Mars now with such a resolution that really help us to investigate the surface with many different, in many different regions that are of interest, especially in equatorial regions where we can look at river flows, at lake deposits, at any rocks of interest. And also a lot of this data help us to define the investigation location for rovers, landing sites, for rovers currently and also for next generation of rovers. On the other hand, the spectral data, these are CRISM spectra. CRISM and Omega have really revolutionized all Mars investigations by analyzing with spectroscopy, especially in the infrared, the surface at a level that is really unexpected, was unexpected 20 or 30 years ago, because we can define, if you look here, this is a spectra from the visible, from 1 micron to 2.6 microns to the near infrared. You can see absorption bands. This absorption band corresponds to water. So within the rocks, not liquid water within the rocks, and these absorption bonds correspond to metal OH bonds, which define different minerals. And so these minerals have been found on Mars, and of course you recognize here the names of phyllosilicates, clay minerals, have been found a lot at the surface of Mars. So this is of real great help to understand the environment of the surface. The next, how to analyze Mars in situ, is the next step. And from Viking in 76, which were the two first landers, to the most recent one, and Perseverance is not on the picture, but is similar to MSL. There is really an evolution of the type of material we send on the planet. And of course, when we are on lander, it's very different than being able to move around. So the NASA agency has developed rovers from very small ones, Pathfinder, just as an engineering test at this time, to MSL, Curiosity, which is 900 kilograms, was sent already 11 years ago to Mars, and is now still capable of analyzing Mars. It has made more than 30 kilometers at the surface. In between, the Mars, Opportunity, and Spirits were kind of halfway. Still 5 instruments, 6 kilograms of payload, but you can see the gap here of size is really the gap of payload. We needed to have a really better payload on the rovers to enable better science investigations, and especially the instruments for exobiology require a lot of weight. When you are on board a spacecraft, whatever it's an orbit or in a rover, you need to have light instruments. And these instruments, there were 2 instruments, very light ones on Pathfinder. On MSL, there are 10 instruments, and the heaviest of these instruments, called SAM, is 35 kilograms. It's half of the payload. And that's really the one devoted to organics. So MSL, Curiosity, and Perseverance is the lightest one. We will discuss that also, which landed 2 years ago. So of course, if Opportunity here, this is the first image of Opportunity in 2004. Opportunity landed in the middle of sand, but just with layers, sedimentary layers 10 meters away. And can you imagine if Opportunity was a lander? The lander would have sit in the sand, analyze sand, and be very frustrated not being able to analyze the rocks just here. So rovers are really keys in understanding the geology of planets, because we can move and we can circulate in different type of environments and type of rocks. And that's really something which has completely changed our view of Mars. So now we have a good set of landers and rovers at the surface of Mars. Some of the recent ones, Zhurong from Chinese, they have very interesting results, mostly for modern environments. I've not included any new results, but if you're interested, it's nice to see they have been able to identify some aqueous minerals in nearly modern environment, I would say, which means modern on Mars can still mean 2 giga years, 2 billion years, but it's still something interesting. We will discuss in this review about Perseverance, about Curiosity, both landed in craters, J0 crater for Perseverance, Gale Crater for Curiosity. So Perseverance is 2 years old, Curiosity is 11 years old. InSight, I will not talk about that. It landed in a volcanic plain, and it's mainly devoted to geophysical and atmospheric investigations. And from the older ones, Pathfinder is here, and Opportunity is here in the Meridiani Planum location. That's the one I showed the image just earlier. And Spirit has been landed in Gusev already 19 years ago. I will discuss that a little bit. And from Viking images, at the first look, of course, Mars is very, very dry, very cold, and this is current investigation. But at that time, this is very old investigations in the current atmosphere. And at that time, scientists were really did not know if life was present on Mars. It could really have been there, and it's really the first time that we had some instruments able to land on Mars. And so they defined at that period 3 experiments to detect light. And there is these 3 instruments were using the regolith around the rover. So it's really defining life, modern life, current life on Mars. And they were set so that they were either interpret the signal as positive 3 times or as negative 3 times. But at the end, 2 were negative for life, but 1 was positive, the one in the middle. And these people still think that they found life on Mars, really. And they even published some books about that. So it's really important to really set the good instruments to be sure of what we can find on Mars and not detect a signature of life that are faint, because this has been explained now by oxidation processes in the ground, in the regolith, but it's not life at all. So that was a long time ago, more than 40 years ago. And the basics still the same, is that here they use a lot of pyrolysis, so they heat the soil, so they heat the ground, and by step they get the gas which come from the ground being heated, and they analyze the gas after. So, and this method has been kept with the Curiosity rover, recently in the instrument SAM. And SAM is a much more perfect instrument compared to those sent on Mars in 76. SAM is really a gas chromatograph coupled with a mass spectrometer and is enabled to analyze organics. So this is an instrument, I will not talk much about it because organics is really not my specialty, but it's really the most important instrument on board Curiosity. Now, if you look to Curiosity, what a geologist needs is really 3 things. It's the texture of rocks, so the images to define the facies of rocks, is the chemistry, elemental chemistry, and the mineralogy. And so these 3 very important investigations are made by different instruments. Of course, the mass cam instrument is a camera, which gives very nice picture. ChemCam is an instrument which has a camera, but also a laser. It was named yesterday LIPS. This is a technique which is a laser-induced ablation spectroscopy, breakdown spectroscopy, which breaks the rock, ablates the rock, and from the plasma of it produces some photons, and the wavelengths of photons correspond to the material, which is to the elements which is in the rock. And this is analyzed by a spectrometer which is on board ChemCam. So this is very efficient to analyze the major elements. And we have another instrument called APXS, which is related to X-ray chemistry. And we have also a microscope taking the texture as well. And the instrument for mineralogy is ChemIn, which is an X-ray diffractometer. So these instruments all still work on Mars after 11 years at the surface. And in addition to the geology instruments, we have also environments with RAMS, which is a weather station, and RAD, which detect radiation in preparation of future astronauts. So this is how a payload of a rover is defined, enabling geologists to analyze the different techniques required to define, to interpret the environments from the rocks they visit. And this is also where Perseverance has been set by exactly the same principle, looking at the geology with texture, facies on one hand, chemistry, and then mineralogy. And actually, our instrument SuperCam is now able to do the 3 in a row, because in addition to the LIPS, which is chemistry, and to the imager, there is also mineralogy enabled by reflectance spectroscopy and Raman spectroscopy. And on Perseverance, a difference is that there is no instruments on board like SAM and ChemIn on Curiosity. There is a sampling system which collected by the arm here, and we have now collected a good set of samples. I will talk about that later. And the instruments which are the most powerful are those on the arm, which are Pixel for the X-ray spectrometry, and Sherlock, which is a UV spectrometer able to do Raman on rocks, with a camera called Watson, which is a small, like a microscope. So this set of instruments is very powerful as well, but there is no the SAM instrument on board Curiosity is not there, so the ability of Perseverance to detect life is a little bit different from Curiosity. That's something to take into account. Okay, so that's how we work with rovers, and all the instruments work in concert to analyze the rocks in the surroundings of the rover. And the one thing I should have said earlier is that at the difference from Viking, which landed in plains which are really volcanic plains, very a lot of regolith, not very interesting for geological perspective on sediments. The sites selected for the rovers are very interesting for sediments because those sites have been selected thanks to morphology and to the presence of aqueous minerals from orbital data. So this is a strong difference, and also that, contrary to Viking, it's not the current environment which is under investigation, but mostly the old rocks, so the past environments that we can deduce from the ancient sediments. Okay, as on Earth, we use sediments as a record of past environments. So to start now with the data we have on Mars and start with aqueous sedimentary environments, just take a minute to look at this image deeply, think about it, look at it. I like people really being able to digest the image because I know it too much. So look at the crater. These are trough depressions, so you can see the light come from up. So this is a plateau which is high standing, and from this plateau you can see two sets of valleys. One set of valleys joining together here on a relatively steep slopes, and to the north here another set of valleys joining together. And when you have valleys joining together like this in a network, on Earth it's very clear it's an hydrological network, a watershed. And that's on Mars, and that's an ancient watershed. Of course dry now, no more water, and it's 3.8 billion years old, so it has been sometimes eroded and also filled by sand in the middle, so you don't see the hydrology so well because you don't see the channels here, but you really can see the different valleys connecting together, which is typical of precipitation. So what we deduce from that, and it's really a short summary from a lecture which can take 1 or 2 hours, okay, is that the geometry of the dendritic networks in Noachian terrains of Mars favors precipitation because all heads of these valleys are scattered everywhere. They are not just punctual as it would have been if valleys was coming from local springs or below glaciers. Here we have valley heads everywhere, and especially coming from the upper part of the location. When I say precipitation, it does not mean rainfall. It could be snowmelt, and it's very difficult to discriminate between rainfall and snowmelt. It could be very important because a climate with just a little bit of snowmelt seasonally in summer and the rest of the year frozen, it would be very different from a climate with rainfall. But something very hard to tell at the scale of what we are looking from orbit. And even on Earth, it's difficult to say when you have the sediments because when you melt the snow or ice from glaciers, when the water is in the system, it does not remember if it was once a droplet, a flake of snow or a piece of ice in a glacier. So it's something really tough. And in order to create such kind of watershed, you need liquid water to be stable, at least seasonally, and over geologically long periods. When I say that geologically long, it means typically more than 10 or 100,000 years. That's a minimum to create this type of erosion. You can create very strong erosion on Earth as on Mars if you have a very strong discharge rates, punctual discharge rates, such as from a glacier just discharging once. But that's not what we see here. You need something really sustained. And when you look at Earth, how long it requires to form such kind of watershed, you usually end up with that as a minimum, which does not mean it's a maximum. It could be several million years. but that's something which is very poorly known as well. And when we look to the watersheds like this, all over the place on Mars, this is in red and yellow, the highest density of distribution of these valleys. And you can see they are all around the equatorial region, which correspond to the ancient terrains. The crater terrains are all over there. The northern plain are very flat and most recent. And don't pay attention to the dark blue here because those are very, very low density. Usually this corresponds to outflow channels just with one channel. So it's very different process than the places here. So where we see these landforms, it's mainly limited to the Noachian and early Hesperian, so 3.8 to 3.5 billion years. Also, there are some exceptions. We have local patches of rivers more recent than this, but usually it's because they are patchy and they are located around craters or volcanoes because perhaps snow was heated locally. But that global distribution is mostly located in this period, Noachian to early Hesperian. And so to get the hydrology then, you need to really look a little bit more into detail in some places. And because it's old and it's covered by sand in many places, there are only a few locations where within the valley you can see the past river. I mean the channel in which the river was. So this location here, for instance, it's less than 200 meters wide. It has the size of a river. And if you calculate the discharge rate, it's at the discharge rate of typical river on Earth. So in order to carve such valley, which is 4 kilometers wide, 1 kilometer deep, you need such kind of river acting a long time to really able erosion that much here. So this also ends up with duration of typically more than 10,000, 100,000 of years. It is observed on Earth that canyons require such kind of time at minimum. And it's always a minimum. We don't know the duration. So when we look at channels on Mars, on Earth first, and then on Mars later, the environments of channels are somewhat different depending on discharge rates. When discharge rate is very low, we have anastomosed channels like this, which do not move at all. It's very, very stable flow and very flat surface. I've not seen any on Mars, so we just stall on that. Don't pay attention too much. The two main processes are meandering channels, which correspond to low to medium discharge rates, and braided channels, which are high discharge rates. And so when we link discharge rates to the gradients, to the slope, you can see here anastomosing, very stable, very low discharge, meandering, and they braiding. Okay, they're all aligned along this slope. And so when you have a strong discharge rate, you can have braiding, even the slope is low, but in general, braiding is when the slope is higher, and meandering is more in plains where the slope is lower. So in general, braided strings are very dynamic. Typically, you can see pebbles, rocks, boulders transported. You have low interest for life development or preservation because it's too dynamic to really preserve material. When it's meandering or anastomosing, then the flow is less dynamic. There is a higher interest for life development and preservation, especially in plains close to meandering system. You have often avulsion of water on the side or flooding. And so this kind of environment could be nice on Mars. And they actually exist. We will see that. And now if you do a cross-section below these rivers, the anastomosing river just stay at the same place. So you have sand and you have clay around. So the most interesting in this kind of stuff is between rivers because you have very stable location with shallow water most of the year. Then in meandering rivers, you have also location with shallow water, but under the river, it's mainly sandy and conglomerates, but it can be very silty or mudstones around in floodplains. And for braided systems in cross-section, it's mainly sandstone and pebbles or conglomerates, so it's more dynamics. So we are looking more for this kind of stuff on Mars to find stable accumulation, stable environments with not too much dynamic environment. This is an image on Earth where you have fluvial beds, dynamic environments, you have conglomerates, but in between two layers of conglomerates, you have this yellow layer here. which is mudstone. So it's typically that's a flood plain just next a fluvial river. So it's a quiet environment of deposition with mudstone, siltstone. That's typically where you can find life. In such kind of environment, you first go to this kind of location because this is where you think the environment was more quiet to depose and preserve the material here. Okay? And on Mars, all of that exists. To the right, you have a meandering system on Earth, and you have dead meanders sometimes. And here, this is a meander on Mars. You can follow it here. So, and here, the light comes still from the top left. So this channel is actually inverted. What does it mean? Inversion of relief is when you have something stronger being less eroded than the material surrounding. So you don't, you see it well, it's a relief, it's a ridge. It just because it was a channel, but the material is more stable, more compacted, more cemented, so it's more efficient to be preserved compared to the softer material around. And you can see even some places, if you follow the river here, it cuts here, and this is a dead meander once. This was a dead meander. And between this material, you have filling here. This is a meander which extended. You know, a meander just start like a small curve, and then extend and extend more and more. And this is exactly what we see here. So you have a plain, an alluvial plain, which formed by meandering system of river, which progressively fills the material here. Okay, and this requires really a lot of time again, and also a sustained activity of water. You can just need summertime may be enough. We have example in Siberia of such kind of channel, but we need water to be stable. Very different from today. Another type of fluvial and alluvial environment correspond to alluvial fan deposits. So fan deposits, as you can see on the example on Earth here, correspond to something in which you have deposition of material very close to the source, especially when you have a difference of slope between a mountain and a flat basin. That's typically where you form them. And you can see to the left a fluvial fan here, depositional fan. You can see here also channels have been inverted by erosion. You can see them. And this is 20 kilometers broad. Okay, it's a big one compared to that one on Earth. On Earth also exists very big fans, okay? But those on Mars are very impressive, and they are really formed by the erosion of this material here. And this is especially the case with an impact crater where you have steep slope and then a flat at the bottom of the crater. And those alluvial fans can form. Here, two alluvial fans extend within the Hesperian. Probably some of them are very Amazonian, so some of them are a little bit more recent than the fluvial rivers, and we don't know exactly why. Perhaps it's related to the fact that the crater itself has formed some of them. And they really form a fluvial deposition without lakes. Does not mean there was not lake at some point, because, for instance, in this example of Death Valley, you had a lake at some point after the end of the alluvial fan, but you don't need to have one. And on Mars here, you don't have sign of lake here. It's really a deposition of the water from a river system depositing here. But it's interesting because it's really signs some very specific type of processes. So here too, like in the braided system, it's mainly conglomeratic with pebbles, so dynamic, energetic environments in these locations. But when we go down and down from alluvial fans, it could be more quiet. If we look to a cross-section here on Earth, this is in southwest USA. It's a cross-section through an alluvial fan, which has been dissected by a river. You can see pebbles. So it's a big mess of pebbles and clast all together. And some of them can show the shape of channels. But overall, it's a dynamic environment still. So it's not the best place for preservation, but it shows that there was water there. And it's also of interest because it's something we have been taking a look at with Curiosity rover, because Curiosity landed in Gale Crater, this big crater here. And this big crater displays a Lanuvian fan. So there was two reasons for landing in Gale Crater. One was this fan on the river, but the main one was the presence of phyllosilicate and sulfate at the base of this mound called Mount Sharp here, and we will discuss that later. But the landing site was very close to the Lanuvian fan, or possibly in the distant place of the fan, as you can see here. And I take profit also of this image to show you that the fan has a very stable, slightly concave profile in topography. Okay, that will be very different from a delta deposit that we will see in a few minutes. And what we have been able to see with Curiosity rover already 10 years ago is this kind of stuff here. You can see pebbles, few centimeter thick pebbles, and look at them. Those are imbricated. Imbricated means they are piled up together, showing the flow direction from here to there, and that's typical of fluvial deposition. Okay, so we know that these conglomerates on Mars have been formed by fluvial deposition, and with the size of the conglomerates, the size of the beds, we can define the discharge rate, which was probably around a few cubic meters a second, which is a small gully. It's not a big channel. So it's already something very far from the main Lanuvian fan, close to the bottom of the crater. And to the left, you have another system, which is more a sandstone with a few pebbles, and you can see cross-bedding. And this is also a sign of dynamic regime, but lower regime than with pebbles, just a few cross-beddings and quiet deposition. So we are in a shallow river system with just quiet deposition. Imagine a river of several meters long, meters wide, and bed forms are just a few centimeters. So it's a quiet river deposition. So still, it's interesting for the environment. It's not the perfect environment because it's still a little bit dynamic compared to what we need to find something very stable, shallow water without activity. So that clay mineral, for instance, can settle in. But this is where we came in after having visited the fluvial environment. So the landing site from Curiosity is here, the Bradbury landing, and you can see the rover tracks here. Okay, conglomerates have been visited in that location, and the fluvial sandstone have been visited here. And you can see there is a distinct albedo right of that location here, and those have been shown to be mudstone. Not from orbital data, it was not possible, but by the rover, looking at the location, we were able to see rocks which are really devoid of any grains. No sand grains, no pebbles, and the investigation from the MALI instrument, which is the highest resolved which are the highest resolved images from the MALI instruments, it's possible to see grains starting at 60, 70 micrometers. So we cannot say it's a mudstone, but it's a mudstone or a siltstone, because sandstone, the limit of sandstone is usually around 60 micrometers. We have not been able to see any grains. So it means it's either a mudstone or a siltstone, which in any case means a quiet settling environment. So an environment which is different from the rivers I've just shown. And this is where the first samples, the first drills were made with Curiosity. And this is the location where these drills were taken. Just above, you can see these are the fluvial sandstone, and some of the conglomerates lie over there. So there is a logic here to have the fluvial environment just nearby, but as for the Lanuvian fan I showed you in Death Valley, you could have lakes shallower or at a lower elevation than the Lanuvian fans, and this is what we see here with some of the mudstones. Now, this is the facies and the texture, but when we go a little bit further in depth in the measurements, thanks to the drills, it was investigated both the chemistry and the mineralogy. And the mineralogy is really interesting in this location. What you can see here are the different minerals from two drills, John Klein and Cumberland, which are in the mudstones, compared to Rocknest, which is a sand dune just nearby, which is close to typical mafic terrain on Mars. You can see in the two drills within the mudstone, we still preserve primary minerals. Those have huge chance to be detrital, and they correspond to plagioclase. But olivine, phospherite, olivine is almost not present, while it was present in the sand. Augite and pigeonite and orthopyroxene, all of these correspond to pyroxenes. They are present, but not in a lot of abundance. And apart these primary minerals, you have other minerals here. I will start by this one, smectite, because this one is very important, clay minerals. We have 20% of clay minerals in these rocks. So they include water, and they're also very important to preserve organics. In between here, you have several minerals, magnetite, which is reduced and contain iron, and pyrrhotite, which is reduced and contain iron and sulfur. And in between, you have anhydrite, basanite, acagenite, which are three sulfur species oxidized with chlorine for acagenite. Sorry, acagenite is not sulfur rich, just chlorine, but iron rich. And anhydrite and basanite are two levels of calcium sulfates. You know, gypsum, it's typical calcium sulfate. Anhydrite is devoid of water. Basanite is one half water, depending on, and it's quite variable. Those ones may be diagenetic. We will see that later. But in all the case, this is really a mixing of minerals which are detrital, but also likely to be autogenic, because we have different species here that may not come from detrital deposition. For the clays, we don't know. We are not sure. Some could be detrital, but the fact that we miss olivine and we have relatively low abundance of pyroxene, it's really possible that the clays correspond to the degradation, alteration of some of the primary mineral, especially olivine, which is the most alterable mineral. And so were formed during the water activity or at depth during diagenesis, but in relation with the lack of olivine of that rock. A last point corresponds to the last line, which are amorphous phases or amorphous component, because they are not really phases. We don't know what is it, and it's everywhere on Mars, and it's an active piece of research currently, because these amorphous phases perhaps could include some of the organics that were found by curiosity. I will not talk much about that, but it's something really important, because they are still preserved while the rock is 3 billion years old. Okay, on Earth you never have that preserved for such old material. You really have them in recent soil, for instance, where the phases have not been formed well because of low temperature, just forming amorphous phases, amorphous component before forming more stable phases. But it's really clearly under assessment. It's not fully understood yet. So what we see here is that we have many different minerals. Some of them are reduced, some of them are oxidized, and we know on Earth that we have bacteria which use sulfur as energy sources, especially with bacteria that reduce sulfate from oxidized to reduced phases, using the free energy, Gibbs free energy to find energy. So we have this kind of differences between the reduced and oxidized material here. And with the SAM instrument, it has been found that there are carbon species in these rocks. So SAM, as I said initially for the Viking instrument, it heats the rock from ambient temperature to 800 degrees here, step by step. And at each step, it analyzes the gas produced by this heat. And the species which are released progressively, the volatiles which are released, you can see there are some species such as dichlorobenzene here, which contain carbon and chlorine. And you also have oxygen, sulfur, etc. But these ones are really important because they sign the presence of carbon species. So we not only have interesting chemistry, but we also have organics here. We don't know where the organics are, and perhaps they are in the amorphous component. We don't know. But at least we have this present in the rock. So when this paper came out, an habitable fluvial lacustrine environment at Yellowknife Bay, it was say, okay, this is one more lake on Mars, one more water on Mars. No, not just water. It's really, yes, a paleo lake with water in a quiet environment. This is where we look for habitability on Mars. It's typically this kind of environment. But we have also carbon species, including organic residuals. We have almost all knobs, perhaps not the nitrogen, but at least we have many pieces of life in this rock. We have reduced and oxidized species with sulfur, which could give energy. Of course, bacteria should have been there to enable to get use of that. It does not mean that life started there. It could just use the environment. And also we have clay minerals, which are, of course, sign of water, but also good for organic preservation. So all of that makes this location very specific and very interesting for habitability on Mars. And pay attention if in the case you find some paper looking at this location here and saying it's a bottom of like a seashore on Earth. You have a lot of fossils, eukaryotes production here. There has been a lot of paper with very strange results that have been published in sometimes good journals, sometimes really bad journals. But take care to what is written about Mars on this location at Gale Crater. It has been interpreted because there is a lot of strange structure which correspond to diagenetic filters. We will take a look to them after. And those are really just chemistry or does not need any organic complexity like in this paper. But it's something that is really that has been produced in the literature, which is not expected. Okay, so coming back to the theory of the lake at Gale Crater, it's clear that the facies, which is key to present for the presence of a lake, is a fine-grained material like a mudstone. And later on, during this mission, we have found a lot of them. Parallel bedding, as here, with centimeter thick parallel beds, and show lamination like this with very, very parallel beds. So when you can see here, it's just because the topography changed, and you can see those are very parallel together. And millimeter size lamination. So these are either lacustrine, shore, or fluvial landmasses with shallow water. We have crossed all of these environments with curiosity so far. Locally, we have found drying out of the lake. That has been observed with mud cracks. To the left, it's deposits on Earth with in the Permian, which correspond to mud cracks in a laguna behind the sea. And this is at a location observed by curiosity, which you can see the presence of mud cracks exactly as you wait for mud cracking in a desiccating lake on Earth. Except that there are some light tone materials, those are diagenetic, just reused pre-existing crack, but are not linked to the same episode of cracking that we can see here. So local drying out, we have also local enrichment in halite and calcium sulfate, which could be linked to local desiccation of the lake. And overall, something also interesting is the chemistry that we have recorded through all the section. We have analyzed more than 300 meters of these lake and fluvial sediments, and where we stand now is still different, but still involved water. And what is interesting is that we have been able to analyze a lot of rocks. So all the circle here correspond to an average of one observation from ChemCam. It's one rock, one bulk chemistry of one rock. It's a CIA index, which nothing to do with the CIA in USA. It's the ratio between aluminium and this cation, calcium, sodium, and potassium. And because those ones are mobile, with alteration at low temperature, this index indicates alteration in open conditions at the surface. By comparison, if you have hydrothermal alteration, it would remove also aluminium, and then you don't have a CIA index showing up in hydrothermal alteration. It only shows up something when you have alteration at the surface. And we observe significant alteration when you increase about 50. Actually, below 50, the CAA just means an average rock composition without substantial alteration. But above, you need to have an alteration explaining the difference in chemistry. And so typically on Earth, we can reach 100, okay, on CAA in tropical areas. But if you look to Iceland, in Iceland you have typically 50s, between 50 and 70. And this is what we have here. So it does not mean a strong alteration, but it's still an alteration related to surface water. And where we see that, we have several drills. And look at these drills. They all show in green a proportion of clay which is from 15 to 30%. So there are a lot of clay minerals in these rocks. Okay? We still have some detrital material, but not that much. And we also have hematite, which signs probably an oxidizing environment and not a reducing environment, which is somewhat surprising because there is this debate that Mars was reducing because there was no oxygen, there was CO2 atmosphere, perhaps even with more hydrogen. But it's unclear. We have a lot of oxidation, and we don't know if this oxidation was really always at the surface or was also during the diagenetic episodes after the burial of these rocks. Also of interest is that the phyllosilicates found are dioctahedral aluminum 3+ smectites, which means something because usually from orbit we have two types of mineral, and some of them are magnesium rich, and magnesium rich could be just diagenetic, and they may not need any alteration at the surface. But we have this aluminum 3+ smectites, which is like an aluminum-rich nontronite, fitting some of what we found with orbit. It's really something which requires surface alteration. So this correspondence between chemistry and mineralogy is really consistent with an open system alteration. So not only we have a lake, but we have also some chemistry going on. The only thing that we have in a sediment, and because we are in a sediment, we are not able to say that the alteration was going on within the lake or was going on before the lake formation in the watershed, and just the transport of the clays removed all the material that piled up in the lake. And what we have is a signature of all these type of environments. That's a limitation of what we can do with the sediments. We will need a piece of sediment on Earth to really solve all questions here. Gale Crater, we have been able, with curiosity, we have gone through along these dunes. We have crossed this plain. We have gone through this hematite ridge that we will discuss later. Through the clay in it, we have gone along the location called Pediment to the left here. And now we are somewhere close to the bright arrow here in what is called the sulfate unit. And this is where we stand with the rover. This is one of the recent images. We have very nice hills which indeed contain sulfate, but also contain size of water from the fascia. So it's very interesting that we are now in the sulfate unit, and we can consider the environment, the chemical environment is probably different from what we have visited first. It's probably a sign of the overall desiccation of Mars or increase in acidity that we have more sulfates. But it's completely in progress currently. We are analyzing this environment. At this stage, the environment of stone are planar beds, very typical of lacustrine deposition, but there was no indication of a lake from a macroscopic form, such as a delta, as we have on Earth. So a delta is very different from an annual fan. An annual fan, we have seen cross-section is very slightly concave in topography. A delta is completely different. It's convex with a plane and a delta front, which can reach 35 degrees in slope, because what happens is that the river, you have the turbidity of the river that gets some pebbles shortly deposited on the shore, but also gets some mud deposited more further away within the lake. So this creates this topography which is very different, very distinct. Of course, the Nile delta is a perfect delta, and you can imagine the front is currently within the water. And so what we can analyze on Mars is to look for past delta, because the topography should show them very well. Let's go quickly on how a delta form on Earth. There are three types of regime on Earth. Typically, we have rivers dominated, wave dominated, and tide dominated. On Mars, we will mostly look at rivers dominated because we may not have waves and tides dominated. At least tide, we don't have them on Mars. And then we have three types of delta depending on the difference of density between the water coming in the river and the water present in the lake or in the sea. For instance, on Earth, we have a lot of fresh water coming in seawater, which is salty, and then we have the density of the sea, which is higher than the density of the fresh water. And this creates very specific type of delta. We will not talk about that because it's likely to exist on Mars. At the opposite, we have sometimes heavily charged water with a lot of mud, which are denser than the density of the water in the lake. That can happen on Mars. And there are some examples. For matter of time, I will not discuss them. They can be interesting because they are a clear sign of deposition at the bottom of a lake and not from the, like a delta. So it's something very interesting, but we'll not discuss them. The most classical case is what is called here the Gilbert delta, found by Mr. Gilbert in the 90s. It's a delta in which you have progressive settled of deposition of material like this with a delta plane and a delta front. So this is typical of lake when we have a density of the water which is the same as the density of the river. I mean the water of the river. And this is a sandbox. Okay, it's 2 meters wide. It has been made by I think Washington State. It's very nicely showed how a delta organized. So usually in geology you look from bottom to top like stratigraphy. A delta is very different because you can see, depending on the presence of the river, you can create a lobe at one location, and then you create another river coming here and create a lobe which is actually lower in elevation at beginning and become as elevated at the end of the formation. So in a delta, it's very different from a stratigraphy, what we usually do on Earth, because delta is probably the most complex architecture of sediments on the planet. Okay, the rivers moves from here to there and just fill the gaps of material and then build another lobe. And you can see several rivers can be at the same time. So it's complex and very, even on Earth, it's very difficult to reconstitute the evolution of a delta from the beginning to the end, just by looking at the final stage, because you don't have all the intermediary. But in general, the final topography, when you have a cross-section, and when you have a cross-section from here to there, you have the plain in which you have the rivers, and then you have the below lake deposits, which correspond to the frontier, correspond to what we call foresets, and the bottom sets, which correspond to lake deposits, which are more muddy. And this is of strong interest for exobiology because bottom sets are really muddy and are really very nice place to preserve organics. On Earth, it's where you can find fossils easily in those kind of environments. And usually, from top to down, you have a more conglomeratic material or sandstones, and then you probably move on toward finer grain material. And we do have deltas on Mars, a lot. And they have been identified from orbital data because of this very specific shape. You can see a delta plane, it's flat, a delta front, steep. That's very different from the alluvial fan I showed you earlier. Okay? And so here there was a lake with an elevation corresponding to the elevation of the delta plane. That's very easy. What is not easy is to define a duration about that, because on Earth, this kind of material could form a delta in a few hundreds or thousands of years, but some of them could be very old required more duration. So it really depends on the river and of the systems getting the debris deposited. Pebbles Valley crater to the left here is very interesting too, because you can see the river system with inverted channels, and here it's a meander, and the front is here, but it's eroded. So we have a view of the delta with some internal erosion, and so we see the interior of the delta. Very interesting. It has not been visited by any rover. Also, it was a long time in really an outsider of Gale Crater at the time of the long-site selection. This is a map of deltas on Mars, and deltas are not always marker of long-term activity. Again, they can form relatively quickly. But what is interesting is that many deltas on Mars align close to the dichotomy, so at the step between the islands and the lowlands. But some of them also are present within the islands. So there are a lot of different types of deltas, and we not enter into the detail here. But it's clear that with a number of them, many of them indicate the presence of a lake, okay, without doubt on the interpretation. So it means there are probably dozens of lakes, of paleo lake on Mars, that can be interpreted as paleo lake because of the presence of deltas. We changed decade. Curiosity first finding was 10 years ago. Now with Perseverance, which landed within Gale Crater here, we have a view on another type of material on Mars, especially with the sedimentary fan here, this river, and it was selected to visit this location. And also a strong interest is the detection of clay minerals and carbonates from orbital data. That's the two reasons Gale has been selected. From the beginning, it was very interesting to look at the front of the sedimentary fan from our perspective view far away. We were still 2 kilometers away from the scarps here. This is an angling site. So this is a fan here. This image corresponds to Kodiak residual butte clearly associated to the sedimentary fan. Initially, but removed by erosion. And on the image here, so you can see Kodiak, and you can see the sedimentary fan all over the place here. And at the background, you can see the rim of Gale Crater, which are 1 kilometer high, so much higher than the sedimentary fan here. And so, with the low view, with this view, we saw inclined layer here, which were really of interest, and we have zoomed in with SuperCam. You remember our instrument, which is able to do texture, mineralogy, and chemistry. This butte with a camera, with a panorama, correspond to this location. The elevation here is about 30 meters of difference. So this piece of material is 10 meters. This one is 15 meters. This is 15 meters in elevation, and you can see dipping layers here. So from top to bottom here, you have exactly the shape of the top set, foreset that I showed you earlier with this. So this is from a book made from Earth data with these top sets, foresets, and bottom set geometry. This is what we see here. On the previous image, sorry, should have started here. This is this location, and you can see here top set, foreset, bottom set, and you can see here as well, and with a better view, here top set, foreset. And here there is a truncation which is frequent in deltas when you have what we call progradation, which means that the sediments the rivers were prograding, like the lobes in the movie were going further and further away within the lake. It's what we see here. So everything above this location is fluvial. These are fluvial deposits. And everything below is lacustrine. These are lacustrine deposits with foreset and bottom set. And those bottom set are the most interesting for exobiology speaking, because those are probably the weakest and the finest grain material that we have here. And we can tell the lake level here, which is 100 meters below expectation from orbital data. And the minimum depth is really something like 20 meters. So what we concluded is that there was a lake within Gale, but this lake, at the time of deposition of Kodiak, was closed, which is interesting because there is an outlet at Gale, but this outlet may not have been something permanent, may just have been an overflow. And at the time we see it was closed. And so I have shown a comparison with Gale Crater in India, which is a closed lake system. And a closed lake system is more variable in elevation because of seasonal variation, evaporation, and infiltration. So we have implication on the water chemistry here because of variation in evaporation. So something to think about it when we work on Gale Crater system. And now where we stand, just at the foothill of the delta. Actually, we are now at the top of the delta, and we climbed it in the last weeks. But at the foothill, we made some sampling, and these samples are really probably sandstone, very fine grain, and they contain both phyllosilicates and sulfates. So very interesting material because we know there have been water in the system. So it's perfect location for habitability. So currently, Perseverance has produced 10 samples, actually 20 samples, but 10 samples have been dropped on the ground as a backup. So the reason is as a backup is that in the case Perseverance don't survive in the next years, if it does not survive, it would not be able to give the sample to the Mars ascent vehicle, which will take the sample to Earth once. This mission is under construction, so it's currently expected to be 2028, very optimistically, probably more 2030. And it's supposed to take the samples that we will collect with Perseverance and get them back to Earth. And that's very important because what we do with the rover, with the instruments of the rover, we do what we can, but it's mainly major elements, very primitive mineralogy, it's like when you are on the field, you take one or two portable LIBS or portable XRF, and you take your lens and you do field trips. But then bringing back the samples to Earth would enable much more analysis with microscope, electron microscope, and everything you can imagine, isotopes, etc. So it would be a very strong step in the analysis of Mars rocks, and none of the Martian meteorites are sedimentary. There's nearly 100 Martian meteorites, but they're all volcanic material. None of them are sedimentary. So getting some sedimentary material is really a key to understand the condition of Mars. And the reason we have dropped 10 of them is really to serve as a backup in the case the rover does not survive. And we have collected the first 10 samples double. So we keep on board a combination of the same samples, and we will collect more along the road. And these samples, we have 3 on the delta bottom, 4 on the crater floor, 1 atmospheric, 1 regolith, and 1 witness tube. So it's a kind of minimal number of samples required for a return. Okay, going now to the groundwater. We know on Mars we have groundwater. We have sulfate deposits have been observed in many regions of Mars. And we have a lot of locations where we have signs of groundwater circulation. We do have some at Gale Crater in the sediments I've shown you. We have some veins. But to start with, the first observation of diagenesis on Mars was with Opportunity at Endurance Crater, so already in 2005. What they observed is a lot of different signatures of diagenesis. For instance, you have these concretions here. They have been called blueberries because in the color image they look like blue spots, difficult to see here. But actually they are iron-rich concretions. And they are probably similar to what has found on Earth when you have diagenesis with iron-rich material collecting within small berries like this. And you have also these pieces of material here which are called crystal molds. They look like a little bit footprints of birds. And these crystal molds correspond likely to sulfates because the rocks contain 30% of sulfates. But this mold shows that the crystals was dissolved. And so there has been not just one phase of diagenesis, but probably several phases of diagenesis, explaining that some of the crystals formed and then were dissolved by later phases. And within this environment also was detected jarosite, which is a mineral which forms only in acidic conditions. So it's a very very specific environment which has been found by opportunity at Endurance Crater. So it's an interest for habitability, but it's clearly lower than what we found at Gale Crater or Perseverance, because here we have something really acid, really briny, and with very low water activity compared to Gale Crater or J0. So it's probably lower interest for exobiology, but still one of the past environment of Mars. And you can see already with Gale, J0 on here, we have different environments and different conditions, depending on locations. So you don't have just one early Mars environment, we have several early Mars environments. Another location which is of interest at Gale Crater, you can see all these veins here. I've shown you some earlier. These veins are calcium sulfate veins, mainly anhydrite and basanite. They are very similar to what you can find on Earth as veins here. And those veins have been everywhere with curiosity. We have observed dozens and dozens of veins from the start of the mission. So the rocks have been really submitted to groundwater circulation and even hydraulic fracturation at Gale Crater, and a lot of circulation producing the precipitation of sulfur-rich material as calcium sulfate, not only because in some cases we see halite, fluorite, manganese-rich, zinc-rich concretions all along together calcium sulfate veins. So it's very rich environment, and currently there's no definitive story with Dagelis at Gale Crater because it's really complex. Another example of Dagelis at Gale Crater, it's what we call the hematite ridge. It can also be called Verabin ridge in the literature. It's a hardened reddish hill, and in this hill we have found an enrichment in hematite, not a surprise from the color, but not only in the red hematite. In some cases we have veins with here 1 centimeter thick sulfate vein. You can see all the grains there. We have been able to analyze them with ChemCam. You can see the shots of the laser here. When it's bright, it's a calcium sulfate, and when it's dark, it corresponds to crystalline hematite. And the crystal are really the shape of hexagonal shape of hematite. And we only see iron oxide when you shoot on them. So that's really specific because I don't know any place on Earth when you have hematite crystallized within a calcium sulfate vein. It's a very specific environment. So it's probably because the rock has been submitted to a reducing environment just through the agenesis, mobilizing the iron, and then within the vein, this iron has reprecipitated again. So different conditions depending on time. What I will do, I will very quickly go through the pyrosols and weathering and let you know about hydrothermal environments. It will be a little bit quick, but it's okay. I will skip that and go directly to this, because we have seen we have river valleys on Mars, we have sediments, we have lakes, and what has been found on this map are candidates for weathering sequence. What is a weathering sequence? It's a profile under which you have an alteration of the surface, which is very specific with smectites overlain by kaolinites. That's something you can observe on Earth in some conditions, especially in tropical areas, but not only. And this is what was observed in several places on Mars, these smectites overlain by kaolinite. Kaolinite at the top, and all these terrains have 3.7, 3.8 billion years old. So they are really consistent with the weathering, which is perhaps coeval contemporaneous to the fluvial activity at the surface of Mars. Okay, so that's really an environment which is interesting, and currently we never had a rover exploring this material. Perhaps ExoMars once will land in a place called Oxyaplanum where we might find this type of material, but it's not sure. This material has been observed in Mars valleys, especially where you have kaolinite here and smectite, which have been observed, and kaolinite is above the lower layers with smectite. This is very important for Mars because these terrains are really old, really Noachian, while Gale Crater and J0 Crater are mostly late stage. They are at the end of the period of the warm Mars. So it's very difficult to know all the Mars story without having been in this terrain close to Mars valleys, Oxyaplanum. So That's the goal of ExoMars. We can hope it will make it once, but it's currently for 2028 or 2030, whatever. Another very specific environment for the surface corresponds to coatings. And that's, when I say specific, it's very specific because it's modern. Coatings are not preserved if they are very old because it corresponds to the surface, which is altered, and altered by a varnish of rocks on the rock, which is just a few micrometers. On Earth, we know that the coatings are formed by bacteria in some cases, so it's very interesting for this reason. But pure chemistry can also form that. So that's completely debated on Earth still. A coating is like this, so it's a manganese-rich crust which occurs at the surface, and here it's partly eroded because the rock is under erosion. And we have seen similar things on Gale Crater with a manganese enrichment. What you see here is a ellipse profile with enrichment of the manganese. These are two manganese peaks here, enrichments at depth. So it's very interesting to see this manganese crust here. Sorry, enrichment at the surface and decrease with depth of this enrichment of manganese, probably over just a few tenths of micrometers. And recently with Perseverance, we have seen the same kind of material, which is here, which is a crust of manganese. So you can see the similarities, same scale, and we have ellipse shots showing that it's enriched in manganese. So this is really a varnish formed by some chemical processes which are recent. So we are no more in early Mars because that's preserved from recent time. Of course, some people will say it's indication of life because it formed like this on Earth, but it's probably just an indication of some specific chemistry acting at the surface with oxidation having linked to this manganese crust. It's under study. I think it's very interesting for especially the modern environment of Mars. So to finish with the early Mars surface environment, we know liquid waters are present, and it's clearly not the case today, but we don't know how long. We don't need to have 1.5 billion years of early Mars with matter on Mars. We don't know. We know we need at least several tens or hundreds of years to hundreds, thousands of years to form the sediments we have seen, but we don't know how much exactly. So currently it's totally under investigation how long and how much, what was the amplitude of the warm early Mars. This is one model over several, but I like it because it tries to couple the internal dynamics, the gassing, with the atmospheric models, and it finds periods of time during which you have more than 0 degree of average temperature, which 0 should be somewhere there. And this period, this is a stochastic model. Don't pay attention to the exact timing, doesn't mean anything. But at least you have several periods within an overall era during which you are cold. So it's possible that it was like current interglacial within a glacial stage on Earth, a little bit similar on Mars, but more controlled by internal processes with degassing rather than astronomical control. But it's totally in work and it's totally debated. I think what we have facts is that water was present, the climate was different, but how much, how long, and all of that is not known. And so to finish in the last 2 minutes, hydrothermal environments. I can go quick the first part because I think yesterday the map of phyllosilicates on Mars shows a lot of locations. Many of them are impact craters, as you can see in green here, and many of them are crystal outcrops. So of course we have the deltas, as in Gale Crater, we have sediments, but we have also a lot of crystal location. So we know the crust was altered, we know there was water in the crust, and maybe there's still water in the crust deeply buried currently. And we have a lot of craters excavating materials which show minerals such as prehnite, chloride. Those are all formed at non-ambient temperatures. Those are metamorphic minerals, but they show that there was water at depth. Okay, and that's very, very important because this location at depth could be niche for life. And I'm sure that yesterday Isabel showed some of the work going on with deep biospheres, dark biosphere on Earth, which are all bacteria living at depth, I think till 5 kilometers. I don't know if that has progressed in the recent years, but it seems life is everywhere below the ground. And this is a whole domain which is under exploration, and Mars could be a possibility even for ongoing life currently, because we could have water at depths of 3 or 4 kilometers with a geothermal gradient without problem. And just water life could have been sequestered at depths, at depths, and just live with rocks in the surroundings. So that's unknown on Mars because we don't have any samples coming from there. We will need to have samples close to a recent impact crater, for instance, to know something more about that. It's quite difficult to tell. But we have a lot of environments telling us that the crust was altered, and also impact craters, very interesting, because around impact craters we have alteration. Some of them are linked to ejecta, so it means that there have been some activity related to the impact crater, the central peaks. So the impact craters are also very interesting places to look for life on Mars, because we have, according to this paper, we have a lot of different environments possible within an impact crater touching a planet like Mars. Even today, or even in the recent time, if you have just ground ice and no more groundwater, then you can melt the ground ice and form a variety of different types of hydrothermal environments. And when you think about hydrothermal environments, of course, you can have many things related to life around this kind of system. And currently, no rover has visited this kind of environment on a crater, but with J0 crater, the rover is expected to go around J0 in this location, which corresponds to the ejecta or to the basement below the ejecta. And those locations could be very interesting with that perspective of hydrothermal alteration. So volcanism-related hydrothermal system, we know also that those environments are very interesting, from sinter deposit, geyserate concretion. It has been shown, I think it's still debated, but this paper at least shows that in Australia there is, in Pilbara, some formation with structures which really look like the called terracette that we see in the sinter deposits around geyserite here in Iceland, or in many places with hydrothermal alteration. So I think still debated, but in that case, it's really a typical sign of life form on Earth. And if you go on Mars, maybe we can find the same things. And I've not discussed yet the Gusev crater from in Columbia Hills, so the Spirit rover. Spirit rover landed here in a location where you have bomb sag here, so it's a volcanic environment, not a sedimentary environment like J0 or Gale Crater. And in this volcanic environment, these structures were a lot debated. This kind of nodular concretions here, which are found here, are very similar to what is found around Hot Spring here in Chile. So that has led to a lot of discussion of possible life related to these shapes. Actually, to be fair, we have the same stuff in Gale Crater, and we did not make the same conclusion, because in Gale Crater the same nodules are actually calcium sulfate or magnesium sulfate, but not silica. In Gusev Crater, it seems that there are silica, and they are, by this way, perhaps more interesting for life. But I think chemistry alone can form this concretion. So we must be cautious about the interpretation from geology texture like this. But at least it generated a lot of debate. People wanted to have sample return from Gusev because of that reason. Then there was also volcanism related to a hydrothermal system. We have also lava that can generate a local melting of ice, for instance. So if you think about Mars now, we have ground ice in many places. Then just get lava flows on it, you will melt the ground ice and form liquid water. So it does not mean it's a place where you can collect life easily or start life, but at least if you have life around dormant, then perhaps you can have life again developing in this kind of system. And actually, I was on this lava flow a few months after, just by coincidence, and I've seen it's already greenish, maybe not very visible here, but there was algae on the bottom here. The water was bathable, really nice water, 40 degrees. And there was algae, and in this paper here, they have made the full inventory of going there every year, full inventory of the species which have developed around the lava flows here. So that's very interesting. Typical environment which you have a kind of explosion of life just after the increase in temperature in relation with the presence of the lava flows and the water. So that could be a possibility on Mars in some places, but we just don't have evidence of that at the present because we have not found such kind of environment. Nevertheless, at Gale Crater, the floor of the crater is composed of volcanic rocks, and these volcanic rocks are altered. If you remember the spectra I showed at the beginning, we have alteration with absorption bond corresponding to water, and we have phyllosilicates here, and we have also sulfates in some cases. And this is a perchlorate, and all the white spots you see here correspond to perchlorates in voids and sulfates. So this rock has been altered. We don't know if the alteration corresponds, for instance, to the presence of the lake of J0 related to the delta. That would be an easy explanation. We don't know, but in any case, it's interesting to see that these rocks have been altered. Just go to the conclusion. We have seen at the beginning on Earth, we have this rock cycle, and life is almost everywhere. And on Mars, it's possible that life would be everywhere as well, because we have all these environments. We have surface weathering, we have transport deposition through river, we have sedimentation, we have diagenesis below the sediments, and we have volcanic hydrothermal circulation. And I've even added the crater that we have a lot on Mars and has been a little bit forgotten from the rock cycle on Earth. But when we look to the Arcane on Earth, we should include the impact crater because that's a lesson learned from Mars. There are impact everywhere, and they play a strong role on the geological cycle. So on Mars, we have different environments. We have just not one early Mars environment. We have several environments, and all of them could have been involved at some stage with life. And I hope that we will be able to visit some of the other environments, such as the one for ExoMars in the future, because with just Gale and J0, we have just a few puzzles, a few pieces of the puzzle, but certainly not the full puzzle